So one of the themes of this course that I don't want to get lost in the conversation is the theme that you just had an opportunity to write about and to read what other people in the class wrote about it, right? Which is, what are the real numbers really? Where do they really come from? If I arrive here from another planet and all I know about are rational numbers, fractions with whole numbers on the top and the bottom is not zero. If that's the only world that I know, how do I get from there to an understanding of what the real numbers are and why the real numbers have properties over and above the properties that the rational numbers enjoy? So just for a couple minutes, what I'd like to do is to ask you, based on either what you wrote in the comments that you received or the comments that you gave to other people in reading their writing, what were some of the main themes that emerged in this conversation about where the real numbers came from? So what did you write or what did you read about? To paraphrase that, you're saying that the real numbers are kind of what we get if we fill in the gaps, the quote-unquote the gaps in between the rationals, right? That they're somehow in between, that they can go places where the rational numbers don't. Was there a particular, what were the touchstone elements of this argument as far as the theorems or definitions or principles that we saw so far in the course? What might be a useful tool for communicating mathematically what it would mean to fill in the space in between the rationals? One of the tools that gets us there is the density theorem, right? Q is dense in R. And remember that what the density theorem says is that in between any two real numbers we can find a rational, right? So in a way, density almost gets this question backwards in that it kind of assumes that we first know what the reals are, and then it says in between any two reals we can find a rational. So denseness captures the idea, but doesn't quite capture the direction of the argument we're trying to make here. Were there other themes that came up in either what you read or what you wrote about that explain, based on what we've learned so far, where the real numbers come from? So one other important source of non-rational numbers that we've seen so far is we've seen non-rational numbers, irrational numbers, as roots of polynomials having rational coefficients. So, for example, x squared minus 2 equals 0, right? The roots of this polynomial would be the positive and negative square roots of 2, which we can convince ourselves are not, in fact, rational numbers. What was the important tool or tools that we used to do that in goal number 1? The rational roots theorem. Right? So that gave us one way to convince a visitor from another planet that there is something else in the universe besides rational numbers, that we can write down equations using only rational numbers in the equations, and that the solutions of those equations are not rational numbers at all. So what that does is that gets us sort of one ring further out from rationals. What this does is it gives us the so-called algebraic numbers, which include some irrationals in addition to the rationals. Okay, great. What else? Other themes or things that we learned about in goal number 1 that could help to get to that notion of bridging the gap from rationals to reals? So we have a principle that tells us something about boundedness, right? That unboundedness of the reals. That if we know something about just how unbounded the natural numbers are, then the Archimedean principle kind of gives us this link that says, because the natural numbers never end, we can also make the same argument about the real numbers never ending. But it too, just like the density theorem, almost gets it backwards a little bit. The form of the Archimedean principle that we use most often says, given any real number, we can find a natural number that's bigger. But that, again, presupposes that we know what the reals are. So the Archimedean principle kind of links the unboundedness of the reals, whatever that means, with the unboundedness of the naturals. But we would get that anyway, even just by observing that n is a subset of R. Right? Every natural number is in particular real, and so since the natural numbers have no upper bound, the real numbers have no upper bound. So the Archimedean principle is almost too heavy of a hammer to hit that with. Were there any other principles or theorems or anything else that merits mention here? Because I've got one more that I want to put this into the conversation.
Completeness.
Completeness. So tell me about Tell me about completeness.
That any real number combined with itself will create a real number.
Completeness. We have this set of field axioms for the rational numbers. So add, subtract, multiply, divide rationals. And that gives us a rational. Those are the field axioms for the rational numbers. And what's interesting about them, right, is that we ultimately want for there to be similar field axioms that apply to all the reals and not just to the rationals. And completeness gets us there, but how does it get us there? What is it exactly that the completeness axiom says that helps to answer this question? The completeness axiom asserts that any subset of real numbers, again, that presupposes we know what real numbers are, but we could, because every rational is in particular real, we could add in here any non-empty bounded subset of rational numbers. We could make it that specific if we wanted to. And what it asserts is that there exists a supremum for that set. As long as it's non-empty and it's bounded from above, then it will have a least upper bound. And that the least upper bound of that set is real. Right? And this is the one principle that we have on the screen where the realness is part of the conclusion and not just part of the hypothesis. So for me, when I think about how I would answer this question, the completeness axiom is the first place where my mind goes. Right? Because it allows us to deduce the reality of something rather than assuming the reality of something. And when I say reality, I guess I mean realness, real numberiness, right? The flavor of a real number. And so what this allows us to do, for example, in the mock trial at the beginning of the course, we were thinking about the claim that the number which we represent by 0 point and then an infinite string of nines, right, that number is either less than 1, or it's equal to 1, or we can't really determine. Right? And those are the three different positions that you argued during the trial. And it turned out that the most interesting of the arguments was the argument that we can't even decide whether or not this number 0.9 repeating is actually a real number or not. Because in order to get to that infinitude, right, the fact of somehow putting infinitely many nines after the decimal, we needed to go a lot of different weird places, right? The group that argued this made an argument about infinitesimals. That's kind of this 19th century calculus style argument where whatever this number is, it's so close to 1 that the difference between it and 1 can't even be said to be non-zero. So if we want there to be a difference between it and 1, that difference has got to be something that's not even a real number anymore. And also the Archimedean property surfaced in this discussion in the first week of the semester. That was before we even knew what the Archimedean property said as a class, right, together. So what emerged, what we decided at the end of the mock trial, what we ended up deciding is that whatever this number 0.9 repeating is, it's got to be the largest number that's somehow smaller than 1. And so what we did at the time was we said that argues for defining a set, the set of all rational numbers which are less than 1. We call that set S. And whatever that set is, it's going to be a bunch of rational numbers, and on the number line it's just going to end up here at the number 1, possibly with an open circle, if you like. Right? And that we could just then define this number to be the least upper bound for this set. And the completeness axiom asserts that this set has a least upper bound, which is a real number. So the completeness axiom addresses directly that claim that maybe this number isn't even real by declaring it to be real. By saying that whatever the supremum of this set happens to be, however we choose to represent it, that it has an essential reality to it, right? That a real number exists by definition, which is the least upper bound for this set. So, as we talked about during the mock trial, we can construct a lot of different numbers that we would like to be real in that same fashion, right? The square root of 2, for example, we could define as, or as a supremum of a set E, where E is the set of all rational numbers such that x squared is less than 2. So if I define the set of all rational numbers whose square is less than 2, that's a subset of the rationals, and therefore the completeness axiom applies to it to say that this set has a least upper bound, and that least upper bound, the supremum of E, is a real number. But we would understand that this real number is the square root of 2. And so this same construction can get us from the rationals to the reals, just by saying, you give me any subset of rationals, and I will produce for you a real as the least upper bound of that set. And all these other things here are ways of getting us partway there. It's very tempting to think, for example, that the rational roots theorem and our way of producing irrationals as the solutions of polynomials with rational coefficients, oh, that's what I meant to write there, coefficients, there we go, that producing irrational numbers in that way is going to get us all the reals, when in fact it doesn't. It turns out that not only are the algebraic numbers, the roots of polynomials with rational coefficients, not only is that set not going to give us all the real numbers, it doesn't even give us an uncountable set of irrational numbers. It turns out that the algebraic numbers, too, are a countable infinity, the same kind of countable infinity that the rational numbers themselves have, or that the integers even have. And yet, to get from there to the reals is still a big leap, and it's not anything short of the completeness axiom that can help us to make that leap.